Okay, we're going to start chapter 14 and 15 we put together because 14 is just over acid and base properties, and I think that's pretty much it. And then the next 15 is on titrations and pH. So I don't know why your book splits it in the first place. They go hand in hand. So we're going to put it together. If you have an ion chart, you'll probably need that out, or we'll need to get one.
You could dissolve stuff.
Dissolve metals and stuff?
Yeah.
Probably not. So we're going to talk about just the properties, and there's 3 different definitions of how to determine if something's an acid or a base. And we're going to talk about one of them today. At least one, maybe 2. But acids, they have a sour taste. Can you think of an acid that you would be familiar with that would taste sour? Lemons have which acid in it? Citric? Citric acid, citrus fruit, yep, citric acid. I don't know if pineapple has citric acid also. It has, yeah. I know it's acidic because it curdles milk. Because you know what's really good is fruit salad. You just chop up fruit, and then you pour some coconut creamer, like coffee creamer over it. It is really good. It sounds really weird, but it gives it a coconut taste if you like coconut. If you don't like coconut, you probably wouldn't like it. But you don't want to do that when there's pineapple in the fruit salad because then it curdles the creamer. Reacts with certain metals to release hydrogen gas. So if you put a metal in acid, you'll see bubbles being produced, and that would be hydrogen gas. Reacts with carbonates and bicarbonates to produce carbon dioxide. Turns litmus red. That's what I was going to maybe get out. If we have time later, I found some litmus solutions. I've seen litmus paper, but I've never done litmus solutions, so we'll try changing colors. And then it will conduct electric currents. Strong acids. We will see there's strong and weak acids. They behave like electrolytes. Remember strong and weak electrolytes? When we had the little beakers of water and we put the light bulbs in them and see if the light bulbs would turn on. Conduct electricity, then it would turn on. So strong acids would conduct electric currents. Okay, nomenclature. We're going to talk about how to name acids. They have a couple new rules from when we did all the other nomenclature early on. There's 2 different types of acids that we will talk about. Binary acids what does binary mean? Like bicycle. Has the prefix bi in it too. What does it mean? 2, yeah. So binary means 2 atoms. There's only 2 atoms in the compound. And the cation has to be hydrogen. And then the nonmetal is your anion, like chlorine or fluorine or bromide. It's just 1 atom. And when you name those, you want to add a prefix, hydro, to the beginning, and then end it with IC. So HCl, we have hydrogen and chlorine, 2 atoms. So we add the prefix hydro, hydrochloric, and we change the IDE for chloride to an IC. So hydrochloric acid. There's also oxyanions. Hydrogen is your cation. So anytime hydrogen is your cation, it's always an acid. And then a polyatomic ion, which normally the polyatomic ions have an oxygen, which is why it's called an oxyanion, so oxyacid. But if it has more, so like it have hydrogen, chlorine, and oxygen in it, then you will not use hydro, and you're going to change the ending of the ion. So when you look up this polyatomic ion on your ion chart, then you would change the ATE ending. If that ion had an ATE ending, you'd change it to an IC ending. If it had an ITE ending, you would change it to an OUS ending. So, for example, if you had ClO3 minus 1 is chlorate. If hydrogen is your cation, you would change the ATE ending to IC, so it would be chloric acid. ClO2 is chlorite, and you change the ITE to OUS, so it'd be chlorous acid when hydrogen is your cation. You guys have questions over that? Okay. This is just a table that has several of your acids on it. We'll talk about how we do that. So we're going to name these formulas. So this is where you're going to need your ion chart. Now, all four of these examples have 3 atoms in it, right? We have hydrogen, nitrogen, oxygen, hydrogen, sulfur, and oxygen, iodine, oxygen, phosphorus, and oxygen. So we are going to have to look up the polyatomic ion on your chart. So what, if you have your chart out, what's NO2? Find NO2. Okay, so we have nitrite. I'm going to write that up here. Nitrite. So what's going to be the acid name? Since hydrogen is our cation, we know it's an acid. What did we say? ITE ending changes to OUS. So the name would be nitrous acid. And the second one, we need to look up the SO4 part. What's SO4? Sulfates. So the name would be, we change ATE into IC. And this one, they add a UR in there, so it's sulfuric. I don't know why. Sulfuric and phosphoric. They add the OU and UR to the name. I don't know if it's just because it sounds better. I'm not sure. Okay, IO3 is what? Iodate. So the name of the acid would be what's ATE? We have an ATE ending, changes to IC. So it's iodic acid. No, NO2 is nitrite. It's an ITE. Right, that's because NO2 was nitrite. It had an ITE ending. So ITE endings change to an OUS, and an ATE ending changes to IC.
Will it always have hydrogen?
Always have hydrogen?
Yeah.
Yes, as long as hydrogen, for all of these, hydrogen is your cation. If it were like NaNO2, then we would name it like we normally would, and it would be just sodium nitrite. Okay. But when hydrogen is your cation, then we have to, it's an acid, so then we have these special rules. Okay, H3PO4, phosphate. So ATE ending changes to, no, IC. ATE changes to IC. And this is another one where they're going to add an OR. This part gets added in, just like sulfuric. Instead of phosphoric acid, it's phosphoric acid. Why is there a 3 here? Right. Phosphate has what charge? -3, so we have to have 3 positive ones, so we have 3 hydrogens. So it's H3PO4. No. Let's see what's next. Oh, let's do some more examples. I'll just make some up. Let's say we have H2S. What would that be? It's sulfide, right? So it's only 2 atoms, right? Just hydrogen and sulfur. So that's what the binary acids are. So you need to add a prefix. Do you remember what that prefix was? Hydro, and then sulfuric acid. Okay, so if there's just 2 atoms, or if you look that there's an IDE ending, because we looked up sulfide has an IDE ending, then you have to add hydro and use the -ic suffix. What would be the formula? If I say we have hydrobromic acid, what would be the formula? Well, let's write our charges. That way we can check to know if we have subscripts or not. Right, because, look, we have hydro. We have the hydro prefix, which means it's just 2 atoms. We have hydrogen and then bromide. So bromide is a -1 plus 1, so our formula would just be HBr. Does that make sense? So really, if you have a hydro prefix, then you want to look at the IDE, just the monatomic ion. What if it was sulfurous acid? Well, it has an OUS ending, which means SO3. Yep. H2SO3. It's hydrogens plus 1, and since it's OUS, we have to look for sulfite, an ITE ending, which is SO3, and it had a 2- charge, so we have to have 2 hydrogens, H2SO3. Good. Okay. Some common industrial acids. So sulfuric acid, 47 million tons are produced per year in the U.S. It's used in petroleum refining, manufacture of fertilizer, and automobile batteries. So that's probably the largest production of acid is sulfuric acid. Nitric acid is used to make rubbers, plastic, pharmaceuticals, and explosives. Phosphoric acid is used for fertilizers and animal feed, flavoring agents, and beverages, and pop. And a lot of pops have phosphoric acid in it. Also have carbonic acid. And then hydrochloric acid is used in cleaning agents. If you look, I know one of them is like Barkeeper's Friend, I think, is a cleaning agent that has an acid in it. food processing, maintaining the correct acidity in swimming pools. Bases. Bases have a bitter taste. Did anyone have parents make them like eat soap if they said something bad when they were little? It has a bitter taste. Feels slippery. Soap is slippery. Even if you have a liquid that's not soap and then you try to rinse it off, and if you feel it's slippery, it's probably a base. And then it turns litmus blue. Ooh, that's hard to read. Bases are, they have OH ions, and OH is hydroxide, and you name them normally. So NaOH is sodium hydroxide. We don't have to do anything different like we did for the acids. KOH, potassium hydroxide, barium hydroxide, aluminum hydroxide, and iron. Ooh, iron 3 hydroxide. You remember why we need that 3 there? Right, iron can form 2 different ions, iron 2 and iron 3. So we have to indicate which one it is, and since it's a 3 here, it was iron 3, so it's iron 3 hydroxide. The Arrhenius acid definition is that an Arrhenius acid would produce hydrogen or H3O plus in water. And the reason why this is hydronium. The reason why we interchange these is because whenever you produce this hydrogen, so this hydrogen would be freely floating around, it automatically attaches to a water molecule, and so it makes it hydronium. So if you are ignoring the water, it produces hydrogen, the proton. But if you're including the water in the equation, then that hydrogen will get transferred to the water and make hydronium. Arrhenius bases would produce hydroxide in water. So in water, it's going to take the hydrogen from the water, it's going to attach to this NH3, produce NH4+, and then hydroxide is going to be floating around in there. Okay, we have strong and weak acids. Strong acids means they ionize completely in water. So like hydrochloric acid is a strong acid. All of the hydrogen and chlorine that is originally bonded together are going to separate into their ions, and the hydrogen will bond to the water, and then the chlorine will be floating around separately. So they completely ionize. So they are strong electrolytes. They would conduct electricity. And they have very weak conjugate bases. We'll talk about conjugate bases later. But those are the 6 strong acids. Those are the only strong acids that you'll need to know. All the rest of the acids are weak. So you just have 6 strong acids. Weak acids only ionize to a limited extent, meaning hydrofluoric acid is weak acid. So you put HF is bonded together, you put it in water. Only a few of those will actually split up. The rest of them are going to stay bonded together as HF. A few of the hydrogens will be released and form hydronium, and you'll have a few fluorines floating around, but most of them will stay bonded together. So that's a weak acid. Weak electrolyte, and most acids are the weak acids. And so that's just a table that shows you here's your strong acids and all the weak acids. Okay, we also have strong and weak bases. Strong bases, again, ionize completely in water. They're strong electrolytes, and excuse me, the hydroxides of alkali metals and alkali earth metals. Do you guys remember where those are? The alkali metals and alkaline earth metals. It's group 1 and 2. Group 1 and 2 on the periodic table. So if there's a hydroxide from one of the first two groups, then they would be a strong base, like lithium hydroxide, sodium hydroxide, magnesium hydroxide, strontium hydroxide. Those are all strong bases, and then everything else is a weak base. So this is showing, and we haven't talked about conjugate bases yet, but acid strength goes up, and then the conjugate base would be very weak. Okay, here's a little picture. This is a good diagram of strong versus weak acids, and you can do the same thing for bases. But they have HCl they put into this container with water, and you'll notice there is no HCl. All the chlorines have their hydrogens missing. The orange is chlorine, white is hydrogen, and red is oxygen. And so all of these chlorines do not have hydrogen attached to them. All the hydrogens have, like, here's a hydronium, here's one that has 3 oxygens. All the hydrogens have gone onto the water molecule and formed hydronium. So it's a strong acid. Whereas a weak acid, the green is fluorine, and then white and red are hydrogen, oxygen. But there are some HF that are still bonded together here, but there's a few. There's a very, very small percentage that actually dissociate. So there's fluorine ion, and here's the hydronium ion from that. So this is showing all of the hydrogen and chlorine separate, so we have 2 separate ions in solution now. Whereas in a weak acid, the concentration of hydrogen and fluorine are very small compared to the hydrofluoric acid concentration that's left. Does that make sense? The difference between strong and weak? Okay, so we're going to identify each as a strong or weak acid or base. So remember those 6. Do you remember those? The way I remember the 6 acids, strong acids, and I don't know, you can figure out a different way if you want, but you need to know them. The polyatomic ion of nitrogen, sulfur, and chlorine, so they kind of are right next to each other, nitrogen, sulfur, and chlorine. So nitric acid, sulfuric acid, and perchloric acid, because it's ClO4. The reason why we have perchloric is because ClO4 is perchlorate, so we don't change the prefix. We leave that per part on there, but we just change the ATE, so it's perchloric acid. And then just the Cl, Br, and I right down the line is HCl, HBr, HI. So hydrochloric acid, hydrobromic acid, and hydroiodic acid. So nitric acid, sulfuric acid, perchloric acid, hydrochloric acid, oh yeah, it's short, hydrobromic, and hydroiodic.